Good morning, everyone. Till now, we have discussed first order systems. Till now, we have discussed first order systems, then second order systems, then impulse input, step input for the system responses. Okay, maybe different inputs. So these concepts help us to understand how dynamic system behave when different inputs are applied. Okay, so if you have not watched those concepts, I recommend that you check the previous videos in the playlist because those fundamentals will help you to understand today's topic very easily. Okay. Now, once we understand the basic dynamic behavior of the systems, the next important question is how do we control a system in real industry process? So today we are going to start a new concept called process control using the CSTR example. Okay, now go to the introduction to the process. So here we consider a CSTR, that means continuous stirred tank reactor. So this type of reactor is widely used in chemical industries where reactions occur continuously and mixing is maintained by an agitator or stirrer. In this reactor, reactants enter continuously. The reaction takes place inside the tank and the product leaves the reactor continuously. So now in most chemical reactants, most chemical reactions, temperature plays very critical role. If the temperature becomes too high or too low, it may impact what the impact? It will impact on the reaction rate, product quality, definitely, and then process safety is very, very important. So our objective is to maintain the reactor temperature at desired value. That means how much value we want. Okay, so let's see the diagram explanation, like how exactly we are going to do here. Okay, now let us see the diagram. So here you can see CSTR reactor with a stirred inside. This is what I already mentioned. The reactants enter the reactor with certain feed temperature Ti. We also have cooling water flow W to remove the heat from reactor. At the same time, we can supply heat Q to the reactor using the steam or electricity. And the main variable we are interested in controlling is the reactor temperature T. This is what our objective. Okay. The main variable we are interested in controlling the reactor temperature T. Now let's see variables in control systems. So now let us understand different types of variables involved in a control system. First one is the load variable. First we have a load variables. So these are basically inputs or disturbances. Inputs are disturbances that affect the process, but not are directly controlled. Okay, suppose if you go for examples, that may be the feed temperature, okay, or maybe feed flow rate, or maybe cooling water temperature. So these variables may change, maybe due to the external conditions and disturb the system. That's what the input, that's called the load variables. Then second one is the controlled variable. What is the second one? Controlled variable. Controlled variable. Okay, this variable that we want to maintain at desired value. In our case, the control variable is the reactor temperature. Okay, so our goal is to keep this temperature at the required overheating conditions. Okay, so this is very, very important. That's what our objective. Then the third one is manipulated variables. So the third type of variable is manipulated variable. This is variable that we adjust in order to control the system. Here, if you go for the CSTR example, here the manipulated variable is the heat supplied. Heat supplied to the reactor. This is what. That's called Q. So by increasing or decreasing the heat input, we can control the reactor temperature T. Okay. So then one more concept we should know about it, set point concept. This is what? Set point concept. So now we introduce an important concept called the set point. Now let's see. So the set point here represents the desired value of the controlled variable. That's called our TR. This is called desired reactor temperature. So the control system continuously tries to keep the reactor temperature equal to the set point value. That's called T equal to TR. Now let's see the control logic here. It's very, very important. Now let's go to the control logic. Let's go for the case 1. What is the case 1? If the reactor temperature becomes greater than the set point, that's called T greater than TR, then the control will, what the control will do? Reduce the heat supply. Reduce the heat supply, so that's the one way. And the other way is increase the cooling water flow rate. This is what, increase this cooling water flow. So if you do these two cases, what happen? This will the temperature back down. So that means the temperature will reduce. That's what we want because the temperature is very high. Now let's go for the case 2. What is the case 2? If the reactor temperature becomes less than the set point, then what the control will do? Increase the heat supply, reduce the cooling water flow. So what will happen if you do these things? It will increase the temperature value. That is the one case. And what is the last case 3? Case 3 will be if the reactor temperature becomes equal to the set point. That means T equal to TR. Then the system is operating under stable conditions. That's what we want. This is what our important case for us. Okay. Now let me discuss about all 3 cases. Now we'll go for the implementing control system. Okay. In order to implement these control strategies, we need 4 basic elements of a control system. So these are the basic elements of a control system. So these are the process, measuring element, controller, final control element. So here the process we want to control, which is the what we discussed, CSTR. Then measuring element. So a sensor that measure the temperature of the reactor. That's what a measuring element. Then we have a controller, a device that compares the measured temperature with the desired set point. That's called controller. Then we have a final control element. So here the component that adjusts the heat input or cooling flow to control the response. Okay, this is what these 3 are doing to do. Okay, so what we can say is, so this is the basic idea of temperature control in a CST reactor. Okay, so in the next part, we will see how the measuring element and controller and final control element work together to implement a complete control system. So, in the previous part, we discussed the basic idea of controlling temperature in a CST reactor. Okay, so now we should understand the different types of variables such as load variables, control variables, and the manipulated variables. Now let us continue and how the control system how the control system is actually implemented in a real process. Okay, so here we have the heat sources. This is very important. So let us look at the heat supply term Q. This is a Q. So the heat supply to the reactor can come from two different sources. Okay, one possibility is steam heating, right? Steam heating, where steam is passed through the heating coil or jacket to increase the reactor temperature. Okay, another possibility is electrical heating. That's called electricity, right? Okay, where the electric heat is supplied the required heat. So here Q will be the Q will be the steam or electricity. So this heat input becomes the manipulated variable used to control the reactor temperature. Okay. So now discuss about the temperature signal to the controller. So next we consider a reactor temperature T. The reactor temperature is measured and signal sent to the controller. That's what this job. The control is continuously monitors the temperature and compared with the desired value. That's what the objective of this controller. Then set point. So set point is represented by TR. This is the desired temperature of the reactor. The control always try to maintain the reactor temperature and equal to the set point value. That's what is job. Then we have a measuring element. Now let us talk about this, very important. So in this system, the measuring element is typically thermometer or temperature sensor, right? Or temperature sensor. So the function of the measuring element is to measure the actual reactor temperature and send the information to the controller. Okay, this measured temperature typically represented as a TM. That's what you saw, right? So thermometer measuring element gives TM. Then what is error calculations here? Error will be the desired temperature minus measured temperature. So that this is what the difference between two values is called error. So this error signal tells the control how much correction is needed. For example, if the error is a positive, the control will increase the heat input. That's what I discussed previously. If the error is negative, the control will reduce the heat input. Okay. Okay. So I think again discuss about with respect to diagram explanation. Maybe you'll get more clarity. So now let's look at the control system diagram shown in these notes. Okay. Here we have a CSTR reactor, which is the process. Okay. So the reactants enter the reactor with feed temperature Ti and cooling water flow W. So inside the reactor we have a agitator or mixing. The temperature inside the reactor is measured using the temperature sensor. That's called measuring element, which is the measuring element. The measured signal Tm is sent to the controller. The control compares with the set point TR. Okay, then it calculated the error. So based on this error, the control sends signal to the final control element. Once you got the error right, signal goes to the final control element. What is final control element? What is this final control element? So here the final control element is the component that actually changes manipulated variables. Okay, there's a two possible here. Okay, what are two possible here? If you're using the steam heating, the final control element is a pneumatic control valve that regulates steam flow using the air pressure signal. And if you're using the electrical heating, the final control element is a variable transformer, which adjusts the electricity power supplied to the heater. So final control element is responsible for physically adjusting the process. Okay, so what I can just summarize of this one is the measuring element measures the temperature. Okay, the control calculates the error, and the final control may adjust the heat input to maintain the desired reactor temperature. Okay, So next, the next section we will understand the different types of control systems, such as feedback controller, okay, and feed forward controller along with block diagram representation. So in the previous page, we discussed the measuring element. The main part we discussed about measuring element, controller, and final control element. So we understood how these components work together to maintain the reactor temperature. So now this part we are going to understand different types of control systems and the block diagram representation of a control system. So let's see types of control systems. Okay, let's see types of control systems. In general, control systems can be classified in two main types. One is feedback controller, other one is the feed forward controller. Okay, so let us first look up the feedback control system. In feedback control system, the controlled variable is the measured. What measured? Controlled variable, measured continuously, and the measured value is used to correct the process. So here the system constantly checks what is the actual output and what is the desired output. That's what I discussed in the previous example. Okay, so then it adjusts accordingly. Okay, in our example, if you go to our example, reactor temperature is, so here reactor temperature is measured and that information is sent back to the, this is what measured, right? This is sent back to the controller. Here we have the controller, or maybe this is the controller. That's why called feedback controller. Okay, so here types of feedback control is two types. One is negative feedback controller, other one is the positive feedback. Negative feedback is mostly used in control strategy in industrial systems. Here error is calculated, is TR minus TM, where TR is desired temperature, that's called set point, TM is the measured temperature. So here the negative feedback helps to stabilize the system and reduce the error. Stabilize the system and reduce the error. Then we have a positive feedback. Let's discuss about the positive feedback. The second type is positive feedback, remember always. So here error is calculated is E is equal to TR plus TM. That's called positive feedback. So positive feedback generally makes the system unstable because instead of correcting the error deviation, correcting the deviation, it increases the deviation, right? So practical control systems, negative feedback is widely used. Okay, remember always, it's very, very important. The positive feedback generally makes the system unstable because instead of correcting the deviation, it increases the deviation. Okay. Okay, now discuss more about the feedback controller. Okay, what exactly we discuss? Then we discuss about what is the other one? Feed forward controller. What is feed forward controller? So feedback control variables are measured in feed forward. In feed forward controller, instead of measuring the output, we measure the disturbances and load variable. It will measure the load variable. Here measure the control variable. That means your inputs. So then only the controller take corrective action before the disturbance affect the process. For example, take our system. For example, if we detect change in the feed temperature, that's called TA, or maybe the feed flow rate W. So we can adjust the heating immediately from here itself. So feed forward control helps to prevent the disturbances from the affecting the system. Okay, before we can do here itself. That's called feed forward controller. Okay. Now let's discuss about block diagram representation. Now let's come to the block diagram representation. So block diagram is used to represent the flow of signals in a control system. Okay. So it's starting from the left side. That means first we have a set point value TR. This enter to the comparator. Okay. Then the comparator compares with the set point. This value, right, this is called error. This compared with the set point, that's called measured value. This measured value Tm and generate the error signal here. The error signals goes to the controller. The controller processes the signal and it sends to the final control element, that's called FCE. The FCE then adjusts the manipulated variable such as heat supply. This is what heat supply, right? This is what doing measured. After that, the signal enters to the process, which is our case in CSTR reactor. Okay, forget about this part what I mentioned, but don't remember about this Tm. Okay, so then output of the process is a reactor temperature T. This temperature is then measured using the measuring element and it produces a signal of Tm. Finally, the signal is sent back to the comparator. So this is the form of a closed loop control system. Okay. So this is the block diagram. We start with the process always. So we start with the process always. Okay. Remember always. I'm repeating again. So we have the process. What is your process? Whichever example of CSTR. Okay. CSTR reactor is our process. Okay. Inside the reactor, the reaction takes place and main variable we are interested in is reactor temperature T. However, we cannot control the temperature directly without the measuring it. So definitely the next component will be the measuring element. The measuring element is measure the process variable. In our case, what is the process variable? In our case, the temperature sensor. Temperature sensor is the measuring element. What that is? It may be thermometer. Okay, so this temperature, this sensor measures the reactor temperature and it converts into the signals called Tm. This is called measured signal. So this sent to the comparator. This is comparator. Okay, and this comparator compares two signals. One is set point TR, which is the desired temperature, and Tm is the measured temperature. So the difference between these two values is called error. What we call error? Error equal to TR minus Tm. This is what TR, this is the Tm. So this error signal tells the controller how far the system is from the desired conditions. Okay, so this error signal will send to the controller. So we know about the basic control feedback controller P, PI, PAD. We'll discuss next class onwards, but till I think about this is a controller. So the controller processes the error and decides which corrective action should take in. For example, it may decreases the heat supply to the reactor. That's what control should take care about it. Okay, how it will implement? So that output of this controller goes to the final control element. So this FCE is the component that physically changes the process variables. This is the component that physically changes the process variables. Suppose if you take example, maybe this is act like a control valve for steam flow. Okay, or maybe variable transform for electrical heating also. Okay, so this is what FCE adjusts the manipulated variable. which is the case is the, what is the case here? That is heat input Q. That is the heat input Q. This is what? Okay. So then this is called, after this process, again it affects in the process, right? After change the process, the reactor temperature changes again. So this is a new temperature measured by the sensors again, and the cycle repeats. It again will process changes, then again the new temperature comes, then again it's measuring. This complete cycle repeats always, because the output is continuously measured. The output is, that's called temperature, continuously measures and sent back to the controller to the system. And the system is called, this complete system is called closed loop system. Okay, that means how the things will be there here. First process, then measuring element, then comparator, that's called error, then go to the controller, then final control element, then implement on the process again. Okay, this is called closed loop system. This is called closed loop system. Okay, so now let us discuss about two important types of control problems in process control systems. Two important problems. Okay, in general, control problems are classified into two categories. One is regulatory problems. One is regulatory control problems. The other one is servo problems. That's called servo controller. Okay, here I think we mention here. So first let us understand what exactly the regulatory controller. Okay, in regulatory controller, the set point remains constant. That means the set point remain constant. That means TR always constant. That means the desired value of the control variable does not change with the time. Okay, that means what will vary? Only with respect to TI changes. That means this TI changes. See, we'll discuss about two important problems. One is servo problem, other one is the regulatory problems. Okay, so when you're going for the regulatory problems, that means only set point is constant. That means this is TR. So that means this TR is constant. That's what our objective. Then what will change? The load will changes. That means the T by TI. Here the set point will be constant. That's called regulatory problems. If you go for example, change in feed temperature, change in the feed flow rate, change in the cooling water temperature. Okay, if you see here, what are changing here? So change in this feed temperature, change in the feed flow rate, or maybe the cooling water temperature. So these are the disturbances. Try to move the process away from the desired operating conditions. So objective of regulatory control is to reject these disturbances, and bring the system back to the set point. The same thing for the chemical reactor. Here we want to maintain the reactor temperature T at a constant value, even if these disturbances occur. So the control system adjusts the manipulated variable and brings the temperature back to the desired value. So regulator control mainly focusing on the disturbance rejection. Remember this point. It's focused on the mainly the disturbance rejection. This always take a disturbance rejection. Now let's go for the servo problems. In servo controller, the set point itself changes with the time. Okay. Then what will constant here? The load TA will constant. In servo controller, the set point itself changes with the time. That means only changes the T by TR changes, TA will be constant. Remember always. That means, go 1 second here. That means only changes the TR, T. This one won't changes. That's what here. This T by this TR. So in this case, the objective is set point tracking rather than the disturbance rejection. So the main example of this one, right, for servo problem is missile tracking systems, tracking of the missiles. Okay, what happened by missiles tracking? So it will change every time their objective. That means the set point will change depending on the tracking of the previous missile, like what is the target, right? That's what. Then robotic motion controller or maybe position control systems. So like that, this is the example for the servo problems. Regulator problem, most of chemical industries are regulator problems only. Okay, so in these systems, the desired position or trajectory keeps changing, and the system must continuously follow the new set point. That's what the tracking of missiles, right? Maybe if you see the most of the videos, or maybe when the war comes, right, we are able to see this type of missiles. So the main goal of servo control is accurate tracking of the desired signal. Okay, so what I can say, regulator control deals with the disturbance rejection while keeping the set point constant. What about the servo problem? Servo control deals with the tracking the changing set point. So both these concepts are very important in understanding the how industrial control systems are operate. So in the previous section, we discussed feedback control. Completely I'm talking about feedback, then block diagram, representation, and types of control problems. Okay, and servo control and regulator control. So now in this part, let us understand the important components used in implementing a control system. So especially the control valve, that's called final control element, and controller elements, it's components of the controllers. Okay, so the control valve is called final control element. So the control valve is maybe one of the most important components in a control system. Okay, it's called final control element because it is the device that physically changes the manipulated variable in the process. Okay, manipulated variable in the process. So in many chemical process, the manipulated variable is what will be the manipulated variable? Most of the chemical process, flow of steam, or maybe the cooling water, or maybe some fluid. Okay, so the control valve adjusts the flow rate of the fluid, which in turn control the process variables such as what is it those, such as temperature, pressure, or level. That's what we are going to see in the lab also. Okay, so let's discuss about what exactly working principle of this final control element, or maybe the control valve. Working principle of the control valve. So most industrial control valves operate using the air pressure signals. The standard pneumatic signal range used in industries are 3 to 15 psi. The standard pneumatic signal range used in industries are 3 to 15 psi. So here 3 psi represents the minimum signal. 15 psi represents the maximum signal. Okay, when the air pressure increases, the valve position changes and the flow through the valve also changes. So this allows the control system to increase or decrease the manipulated variable. This is the advantage of this one. So this allows the control system to increase or decrease the manipulated variable. Okay, so What types of control action? What are the types of control valve action? So control valve mainly operate in two modes. One is aid to open, another one is aid to close. Okay. What is meaning of aid to open? That's called ATO. Aid to open. Aid to open. So in this case, when air pressure signal increases, the valve opens. That means, so higher air pressure means more flow through the valve. Okay, that's called aid to open. What about aid to close? Aid to close means ATC. Remember these shortcuts. So in this case, when air pressure signal increases, the valve closes. So higher air pressure results reduce the flow through the valve. Okay, these valves we can see in the laboratory. Aid to open or aid to close. Okay. So now let's discuss the control of the components. Let us look at the main components of a control system. Okay. So typically control system contains several elements that converts signal from one form to another. This is what you can see everything in the laboratory. From one form to another. Well, let's see the first transducer. Okay. So what exactly doing transducer? Transducer converts one form of energy into another form. That's called temperature to current. For example, temperature sensor converts temperature into an electrical signal. This electrical signal is being transmitted to the controller. Second part. So the controller receives the signal from this measuring element. Okay, and it compares the measured value with the set point and it's calculated the error. So based on the error, this controller decides correct control action. Okay, in modern systems, the controller also record process data for monitoring and analysis. Okay, this is what only the 4020 to 4020 current to current signals. So here temperature to current, when you got the current, right, they change just only current to current. So then we have the converter. So what exactly? Sometimes signal must be converted from one type to another. That means we got the electrical signal, that's called current signal, to pneumatic signal. This is what the converter will do. That's called pressure signals. So it will convert electrical signal to the pneumatic signal. So this conversion is done using this converter. And finally, the signal reaches to the control valve, which adjusts the flow rate of the fluid. Flow rate of the fluid. So this changes the manipulated variable and helps to maintain the process variable at desired value. That's what we want, right? Process variable desired value. This is what happening in the controller, inside the controller. That's called components of the controller. Okay, so this is a module which discuss basic concept of process control system, include what is the CSTR temperature control, and then variable in control systems, then measuring elements and controllers, then we discussed the block diagram representation, and regulatory and servo control problems, and role of control valves and control components.